we need to cut the music short. It's a wonderful recording of Vivaldi's Spring. I love it. I hope that you like it too. And yeah, let me say good morning to all the other students. I think Yun Tong, good morning. Zhong Ting, Catfish, hey. And by the way, guys, Catfish call me almost every lecture. Very curious. You have many questions. That's great. Wei Yuan, the dentist was right. I have to say. Yeah, Polly's dentist also say, hey, your teeth are okay. Just keep on brushing and use the flosses after a meal. Hui Xin, good morning. Howard, morning. Yu Jie, Huai morning. Zhao Qi, good morning. Keke, good morning. Yeah, Keke, you seem to remember changing the usual nickname to the full name for the lecture. Thank you. Guan Yu, morning. Cheng Rui, Wei Xiang. Hi, Doris. Oh, really? Oh, surgery? That sounds serious. Okay. I hope it's covered by the insurance, by 健保, because yeah, dentist I think is relatively more expensive to visit these days than going to the hospitals. All right, so hey guys, let's wish all the luck to Wei Yuan. Hope everything goes well. And let's come back to the announcements. So there's nothing more to say than the announcement points yesterday. And I promise you guys that we'll go through all the important points that you guys need to care about the first exam. All right, so let's go over them in detail one by one so that you guys are a little bit more comfortable about taking the exam, all right? So date and time, this is clear. The exam will be on Google Form, and Polly also demonstrated yesterday in the video, right, in the stream, that some of the questions very straightforward, that you just click the option, but some might be a little bit more open question that you need to type up your answer and then explain why, because Polly often asks explicitly, if you choose this, why? That's because usually many of the questions Polly asks, you can actually come up with different solutions depending on what you think is more important. Okay, so tell why. But that reason need to, explain the choice. Right? And there are also questions that you need to go on the programming assignment workstation. Some are for you just to do something, okay? But some are more goal-and related programming problems. But of course, you are asked to do socket or socket-related programming. For this exam, there will be also programming assignments maybe related to PA2 or PA1. All right. So that's the type of questions you might see. And if you are still not very comfortable, and if you find time, you can definitely go to the course page and go to the exam link. Down below here, there are some simple Google form exams. So you can get through and see how much time it would take. I have to say that it depends from exam to exam. Certain exam might appear longer than another. And certain exam, as you work on it, it appears shorter but harder. Okay, so try to work on some of the problems so you get a feeling. Particularly the programming problems. Those problems is usually short, but it might take a long time to really get it solved. Right? So once you work on these programming related problems, then you get a rough feeling that in an exam, how much time you want to allocate to the sort of plain question problems versus the programming problem. So you want to find your own balance, okay, doing these. And so, of course, there are other points. Polly also mentioned in the exam page that you want to sort of know ahead of time, so that the anxiety is a little bit lower, because you know that when you are overly anxious, you don't perform well in the exam. But in the worst case, you know what? Exam is only, I think, 30% of the semester grade. Okay, so try to take it easy and try to do the best you can. The solutions will be available. Simple solutions will be available from the exam page as well. I think you can find simple solutions from previous semesters. Okay, so for example, exam 1, if you click in, okay, this is last semester's exam 1. You will see the questions, and these are identical to the Google form content. It's except that the Google form is interactive for you to read and click or type. Now this is more PDF form. I kind of extract the content, and for each problem, each question, I show simple solutions. Okay. The reason I call them simple solution is that for some problems, some questions, of course there are only one answer for them, but for more times you will see problems, the solutions can be very diverse. All right, so you go over these, you get a rough feeling the problems the students need to tackle last semester. And then you can find exams from last semester or last year. I had all my old exam questions and simple solutions here. Of course, you know that you only have a limited amount of time to work on them. So I would say that try the best you can. And again, take things easy. After all, you are you, right? You don't need to be perfect. It's a little bit weird, right? There's no perfect person, I think. So take things easy and enjoy. And that the exams are opportunities for you guys to know that, hey, maybe you want to pay more attention here, there. And maybe you want to, of course, have the past year's students' suggestions in mind. You want to keep also past year students' solutions for the quizzes there for your reference. But I think it would help better if you try to come up with your own answer. Okay, and only when it's really hard, then you refer to the answers provided by a student senior of you who have already taken the course. I think that will be a better way to go if you want to make sure that you learn the most. Because there are two kinds of learning. I don't know if you noticed. One kind of learning is that, hey, you just kind of need to memorize quite a bit of things for the exams. That kind of learning, I think, as a crash course works. But you will see that memory goes away as well as time goes by. You find that kind of learning goes away real quick. And after a while, you thought, why am I doing here in college? I actually don't know if I really learned anything. Okay, that's useful. So there's another kind of learning. That's what Polly is trying to do here. That's why you guys feel a little bit different taking Polly's course. So I'm trying to show that you can also approach a problem. If you spend a little bit of time thinking about it, paying a little bit more attention, and discuss with your teammates. They might see things differently from you, and then they might pick up something that you did not pick up during the lectures. Okay? And so that's more how people solve problems in real life, isn't it? Yeah, so hey guys, as you're working on the quizzes, of course you can Google as well. That's also real life. I think NTU is trying to make making changes. We need to. So I hope that you find it also something nice to approach, okay, as a slightly different way of learning. So Poly also make sure that you can still earn grades if you are not exactly that adaptive to new learning style. Hi guys. All right, so this is just so that you guys get why the course is designed in a very special way, because NTU, after all, is a university that is hoping to bring up leaders, hoping to bring up young people who can sustain the society. And we do really want you guys to learn how to solve problems in general, not just to get good grades, okay? Hey, getting good grades is great, but you can be even better, okay? Be a really capable, powerful person. All right, so with that said, let's come back to walk through the other important points. So you will also you'll be working on a Google form. You will need to start another window that's running Google Meet, okay? And you will need to have a working camera and stable internet connection, okay, during the exam time. So that internet connection needs to be stable for the Google Meet session, for your Google form as well, and for you to have a terminal or two to work on the programming related problems. You see that stable internet connection, very important. So you might want to also have a reasonably powerful laptop or desktop for the work. Okay. So there'll be a test session at the end of the lecture today. By the way, I think Huaizhi did the testing already early in the morning. Okay, that works as well. If any of you want to do this also in the break, we do have some break time. That is also fine. So once you finish the testing, then you get this peace of mind. Now, the Google Meet session is very important. Although you probably don't speak, you probably won't be looking into the camera, but it's important and critical for fairness reasons, and it's actually mandated by the university. The first reason is this: in case some of you type up questions or ask question vocally, then all the rest of the class can see the question, can hear the question, can see Polly's reply to the question, can hear Polly's reply to the question. So you want to make sure that you can hear things. And when there are students asking questions, you might want to pay attention. Later on, you might run into the same question, and you might want to ask the same question. And you know what? The question might have been answered already. All right. Second, this is regulated by the university. When we're doing exams online, we do need to have a visual eye contact. We do need to have visual interaction there. So for example, I need to verify also before the exam start your student ID, the photo, and what's showing from your camera, right? So before the exam, there'll be some 10-20 minutes. I'll be going through the class row and calling your name, and you would bring up your student ID and show it in front of the camera so Polly can see, to verify you are indeed who you are, right? And that's pretty much the purpose. Okay, so Polly can check who you are, and you stay in view of the camera, and instead of going here, there, talking to other people. And second, of course, you get to use that interactive session to ask question directly, because during an exam, if you need to type up question, usually that takes longer time than just asking straight. Right? I know that some of you might be fluent in English, and it might be easier to just speak the question. Number 4, Yeah, the exam is super long. I know that some of you don't like the fact that you won't be able to finish the exam. Yeah, chances very high that you won't be able to finish the exam. But you know what? That's completely normal. Given how good you guys are doing the exams, this is very, very different. Okay, so I probably also provided something in the exam page of the course website. So if you are not very comfortable for having a closure, finishing an exam, you can find out how one can be trained to try to address that issue. All right. Okay, bullet number 5. It is advised that after you fill the basic information such as your email address, where you would like Google Forms send the submit confirmation email to, your name, your student ID. Right after you do that, hey, submit an empty form, because you see yesterday that you can always click edit my response, isn't it? You can always come back to fill the next problem and the next problem and the next problem. But you see that the Google form, it might catch some of the answer you type before you submit, but it might not. So only after you submit, then you are sure that the solution you type up between the previous submit and this submit are really committed. So my advice is that you try to do the submit at the very beginning. So you can still claim the link for the form in case after you click submit, the Google form does not the submission was not successful and it did not show edit your response link. When the network is a little bit busy or the Google form service a little bit busy, that might be the case. So that TCP connection somehow failed. All right, so right after fill the basic information, submit. But maybe in the midpoint, in the midpoint of the exam, I think I said it here. Please do submit the form multiple times during the exam. For example, midpoint. So Poly would oftentimes sing the midpoint of the exam saying, hey, this is halfway through. You might be doing very well. Commit the change by submitting the form. And then you worry less about whether you miss a lot of the answers you type up. Feel free to do it more frequently, because that doesn't take too much time and you can always be doing some thinking in the meantime. So this is just in case that there will be network outage. So this at the beginning of Poly start teaching online, because this is because of COVID and we all get forced to do this, and Poly find this way of teaching very interesting, and it's actually not bad at all. It's got a lot of flexibility, and it's actually working also effectively for my course. So but at the beginning, the network stability is not really all that predictable, because all of a sudden many people need to use internet to take courses. But as we go on, as Poly go on teaching for several semesters, I find that the network connectivity issues being less. So if you would be using the Wi-Fi to connect, make sure you are close to the AP. The Wi-Fi AP. If you are far, you could see that maybe during the testing that the network connectivity is okay. But in the middle of the exam, the Wi-Fi AP is getting weak. The signal from the AP is getting weak. So that's, I think, the only thing that I see could be an issue. If you're using Wi-Fi, make sure you're close to the AP. If you are using a wired connection, then I don't see a problem with it. All right, and this is bullet number 6. Remember that if you submit late, we'll need to deduct some points. The thing is that Google Form, once you submit, Poly can also see a timestamp of your submission. And that submission will be the time that Google sees that the submission is complete. So there will be some delay between you clicking submit to the timestamp that Poly is seeing. Okay, but after a few experiments, I find that it will not be longer than a couple of seconds. So I'm setting a grace period of 5 seconds. Oh, hi. Some of you probably can't wait to test, all right? All right, so hi. Hello. Okay, so you might be testing, but if you want to stay on the channel, make sure that you mute the volume from the YouTube stream, okay? So, oh, okay, I think he quit. Okay. But if we see the timestamp that's 5 seconds beyond the exam deadline, but within 1 minute beyond the exam deadline and within 1 minute beyond the exam deadline, then 12 points deducted. Now, if the timestamp shows 1 minute to 2 minutes beyond the deadline, then 25 points deducted. Okay, so during the exam, when it's time to stop, you do have the opportunity to hit submit, but you probably want to submit a little bit earlier as well, because everyone will be hitting submit. The server might be no problem. The server might be a little bit busy. So Poly would usually do this. Hey, this is just 1 minute from closing of the exam. So, hey, if you feel that the problems that you are thinking, there's no way of solving it 1 minute, then just commit, okay, and take things easy. Of course, you can stick to the last second, but it's possible that you run into a congestion there at the server. Okay, not really at the network, but at the server. All right, so bullet number 7 is, so there are programming problems. There are also sometimes practical problems. Poly, as she lectures, you see that I show also demos. You're encouraged to try them out yourself, because after all, internet is right there, very alive. We're using it every day, right? As you're learning it, make sure that you know how to play around and discover the properties of the protocol we talk about in the lectures. So the theory side and the practical side can coincide. Okay? So that way you can implement also better a real system. Okay? And for these programming and practical skill problems, you will be receiving your own account. So each student will be receiving your own account, but those accounts are only for the exam purpose, all right? And so that you guys won't be seeing each other's solution as well, okay? And these accounts will be available 1 day before the exam, which is next Tuesday, right? Now, during the exam, you will be allowed only 2 SSH sessions to log on, okay? You really don't need all that many. Okay, and if you log in more than 2 SSH sessions, Poly here will remove the extra sessions. All right. Number 8, the scope of the exam will be PA number 1 to number 3. PA 3 is due this Saturday. As for the lecture material, it will be chapter 1.1 to 1.5. Chapter 2, chapter 1, 2.1, and all the way to 2.5 for now. We'll see if we manage to cover some of 2.6, okay, next Tuesday, and that we can include them into the exam. And last but the least, okay, again, as I said, I was hoping that we could create this atmosphere that the exams are more for you to verify whether you really learned this thing. okay, that we talk about in the lectures. All right, so that should be very clear now. If there are further questions, of course, feel free to ask as you're testing your camera, okay, out at the end of the lecture today. Now, let's move on to the lecture today. We'll talk about Dns and P2p. Now, these two types of applications, you probably heard about them, but these are the things that you don't get your hands on all that easy, okay? And particularly DNS. DNS, very, very important. You're using it every day, but you don't necessarily start an application that says DNS, okay? So DNS is very special. We do have 6 videos, okay, we want to play here. 4 in the first part, DNS, the communication model architecture, and 2 in the second part, the data records and setup. Okay, so let's start with the DNS communication model, and let's start by Polly explaining what it is, what service this is, DNS.
Next is Chapter 2.4 DNS, which stands for Domain Name System. And before we talk about the purpose of it, let's talk about identifying a person. If I tell you my social security number, my name, and my passport number, which one would you think would be easier to memorize? Well, social security number, 10 digits long. Well, the national ID of Taiwan is also about 10 digits long. You can correct me if I'm wrong. Name, Polly Huang. Passport number, don't even bring this up. Polly does not recall her passport number, as a matter of fact. So very obvious, isn't it? The name is so much easier. Well, that's just how human brain works. Name, form of ID, much easier. Number, form of IDs, harder, especially when it's a long sequence of numbers. Well, internet, to identify a machine on the internet, shows a similar obstacle. So hosts and routers, many of them have the IP addresses, right? But these IP addresses are even harder to memorize, maybe harder than the passports. And as you're working on the PAs, right, memorizing the IP address of the workstation, super hard. Even though you've already worked on it for a while, if I ask you to type it up, it's probably still challenging. So what we do here on the internet is to give some of the important machines also a name. For example, www.yahoo.com here is the web server of yahoo.com. So you could just type www.yahoo.com and it quickly leads you to Yahoo's website. Similarly, www.google.com. Quickly, we reach Google. So, hey, how does the web browser know what is the IP address of the web browser given just www.yahoo.com? Well, that is the functionality of DNS, to identify the mapping between the IP address and the name. And let's talk about DNS more formally. So essentially, it's a database of these mappings. So lots of these IP address mapping entries. Nowadays, it's distributed, meaning there are multiple of these name servers, and there's a hierarchy actually connecting these name servers. Some of them sitting at the higher hierarchy, and some of them sitting lower. What's a bit special about DNS here is, if you hear me saying that, hey, a web service will need to query DNS system in order to find the mapping. So, hey, web service is already an application level service. HTTP is already the application layer protocol. So it seems that the application layer protocol, HTTP, there needs to work with DNS, which is also an application layer protocol, in order for it to operate correctly. So DNS, in fact, work with multiple of these application layer protocols, not just HTTP. All right. So name servers there would help all these application layer protocols in order to resolve names to the IP addresses. It's a very essential function. Some might argue that it's one of the core internet functions, which might sit underneath the application layer protocols instead. But now we put it in the application layer such that it's only running on the end hosts. If we need to update, improve the DNS servers, we don't need to actually go ahead into the core of the internet, all these routers, to change everything. So that makes changes a bit easier. Right? So there's a very special phrase that the internet designer would like to say, which is complexity at the network's edge. What it means that if you come up with something, some function that's very essential and it could go complex, then let's put it at the edges. Let's have it running on the hosts instead of running in the routers at the core of the internet. Okay. And a good side of doing this is so that we could evolve quickly and the performance bottlenecks can be removed quickly.
All right, so you know why we need DNS, just to translate from hostname to the IP address, because human beings remember hostname easier. But hey, servers, they are machines. They only recognize a service by the IP addresses. Okay, so DNS. And this sounds like maybe a network, a lower level service, but why do we implement it in the application layer? You see that leaving the complexity at the edge. That's a practice that the network engineers do very often because it's easier to make changes at the edge than in the core, where those routers need to be running 24/7 to sustain operation of the internet. It's not good to take them down and upgrade and put them back in, just like the power system. Now, the next video. What is the nature of DNS? What kind of service quality we should provide, okay, for DNS?
Next is chapter 2.4, DNS.
I'm sorry.
Which DNS services. There are multiple services actually DNS provides. First is what we've talked about, the most basic one, from the hostname to IP address translation. It does 3 other forms of translation. First is the host aliasing. So what happened often on the internet is that some hosts came with host names, but the host names could be slightly longer, indicating where it is or which one of it, number 1, number 2, number 3. Okay, so those can still be slightly harder for users to memorize. So alias name here is often cute and short and very easy to memorize. So this is where the users know the services are, such as .google.com. All right, so from alias name, DNS allow the web browser to look up what is the canonical name of the server, and from the canonical name of the server, identify the IP address through one of these mappings from host name to IP addresses. So that's how host aliasing works. Second, mail server aliasing, right? So I mean, you must have one of these, right? Gmail accounts. If your friend is sending email to your Gmail account, your friend's mail server will need to know who's your mail server. So who's Gmail's mail server? This thing actually looks very general. It's in fact a domain name, not quite a host name. So what happened in DNS is there are also these entries saying for this domain, gmail.com, okay, all the emails destined to this domain should send to this machine, SMTP, gmail.com. This we talked about when we were telnetting to an email server to demonstrate the message exchange there. smtp.gmail.com is the actual mail server for gmail.com. So there are also this entry here in DNS service. Okay, and this is called the mail server aliasing service. Last, okay, this one is a bit tricky, but it's growingly popular. It's called the low distribution service. What it does is this: for a host name, there could be multiple IPs that map to it. So IP1, and then the same host name, IP2, IP3, IP4, and so on and so forth. Okay, what happened here is that the DNS might actually rotate, returning different IP address each time a web browser or an email server looks up for an entry, okay, for the particular host name's IP address. So that way you kind of rotate using different physical machines every time, and therefore distribute the load of the service. Why not centralize DNS? You heard in the previous slides, there are multiple name servers and there's a certain hierarchy behind it. So why not just one? Well, it doesn't take long. At the beginning of the internet, there's indeed just one DNS server. But it doesn't take long that we realize when the machine is off, the entire DNS service is off. And everyone on the internet, unless you can memorize the IP addresses of all these servers, otherwise, there's not much you can do. Okay, it's off. Second, every application that needs to find mapping IP address given the name, traffic needs to go there. So very high volume. It gets really busy at times. And hey, those users that are around this particular server will have short delay, but they will always be part of the world far away from a particular machine. So delay not ideal. Some could suffer forever. And maintenance, this is a tricky issue, but it is indeed a problem. There are two perspectives looking at the maintenance issue. One is that the DNS server software is growingly large. When it grows too large, if you want to make just a tiny little change, you need to what? Turn off the machine, update the code until you can put it back running, right? But all you want to do is just to make a small change. So one small change influences the entire internet. Not good. Second, it's also hard to do the maintenance, right? Because if you want to just do some testing, debugging, you have to take down the entire DNS as well. And when the software grows large, chances are higher that you need to do the testing longer, debugging longer. Not good either.
All right. All right, so in that video, you see that DNS service not only provide host name to IP address mapping, because nowadays these machines on the internet, they not only have a name, they also have nicknames. So you need to do this alias, nickname mapping to the real name, and then from the real name to IP address. Similarly, for the email address, right, you send probably to polyhuang@ntu.edu.tw, but ntu.edu.tw is not the machine name of the mail server. And how do you find the machine name of the mail server so that your local mail server can forward the email to? So DNS is also doing that tracking, okay, from your email's domain part to the mail server of that domain mapping. So you see that the DNS service is sort of growing. And DNS is expected to be very reliable so that it's not possible to maintain one central server for the entire DNS service. And that takes us to the next video. So there is a network of DNS servers.
Therefore, DNS is not a centralized system, but rather a distributed hierarchical system. And this is how the hierarchy looks like. At the top, the root DNS servers. Second level, the .com, .org, .edu DNS servers. The lowest level, or the authoritative server level, the yahoo.com, amazon.com, pps.org, poly.edu, ums.edu. So what you're seeing here is, hey, .com further breaks up the namespace, and each of these servers at the bottom will serve a small range of the names there are on the internet. So distributing the load of the name IP lookup. Now, the process of looking up the IP address in a nutshell is this. Client now wants to get the IP address of, for example, www.amazon.com. What it does is first query the top server and try to find the second level server. Query the second level server, next try to find the authoritative name server, the last level. And then from the last level of DNS servers, finding the IP address for a particular host. And let's talk about each of these name servers a bit more. At the top level, the root name servers. It's connected by the local name server. Now allow me to explain. This local name server is not in the hierarchy. This local name server is actually very, very close to the client. Typically what happens is that a whole bunch of these end hosts sitting in an ISP will be sharing one. So ISP or institutional network will set up a local name server there for all the users in the domain to send the queries. And then this local name server then will relay the queries to all these servers in the hierarchy. Right? So in a way, the local name server here is the client of the name to IP lookup service. So a local name server contacts the root server first. Right? The root server then will contact the authoritative name server to find the mapping. Get the mapping, and then return mapping to the local name server. Now, the trick part is this. Okay, when I say contact authoritative name server, it's not like directly going from the root to the authoritative name server. There's a certain way of rerouting the query until it reaches the authoritative name server. Authoritative name server is really the one containing the name and IP mapping. Okay, the top level knows the second level. Second level knows the authoritative servers. Only the authoritative name servers knows the exact mapping. And you see here, there are not many root servers. There are 13 logical root name servers, but each root name servers now have multiple physical sites. For example, here in Tokyo, there are 5 sites, 37 sites just for the Swedish root server, etc. So there are quite a few in America, but essentially, very few of these root name servers. Next, the second and the third level DNS servers. At the second level, we have a bunch of these TLD servers, top level domain servers. They're responsible each for a different top level domains. So top level country domains as well, UK, FR, CA, etc. So essentially, this is the last part of the host name there. And each of these TLD server is maintained by some sort of organization of public interest. Some people call them NGO. So for example, Network Solutions maintain the servers for the .com TLD server, and EduCost for the .edu TLD. At the third level, we have these authoritative DNS servers, right? So it maintains the IP host mappings. And it could be maintained by the organization itself or by a service provider if the organization is somewhat small and there are not many entries really. Right? Local DNS server, this I tried to introduce earlier. It does not belong to the hierarchy, 3 levels. It's very special. Each ISP or institution network will set up one, and all the clients in the institution or in the ISP will configure themselves to send all the queries to this local DNS server, which is also called the default name server. So when the host makes a DNS query is always sent to the local DNS server. Now, these DNS servers often carry these caches of recent translation. So whenever we get a host to IP address mapping to the local DNS server, of course forward the answer back to the client. But in the meantime, the local DNS server also keep a copy of that, okay, for some time. And this is for the benefit that if the client is looking for the same name again, okay, same name IP mapping again, then it's conveniently already cached in the local DNS server, avoiding going all the way to the hierarchy. So nice. But be careful, these entries could sometimes go out of date. So while these entries are cached locally on the local DNS server, well, the entry might have been changed in the authoritative DNS servers. Okay, although very rare, but there's a chance. So these local DNS servers, if you think about it, it works more like a proxy server. Okay, it's not exactly client, it's not exactly server, it's something in the middle, helping relaying the queries, relaying the answers. Okay, so helping forward queries into the hierarchy if there's no hit here at the cache.
All right, so that local DNS server is more like a proxy server, much as you see in HTTP. And in DNS, the server side, the real DNS server side, there's a hierarchy, right? So root level, and then TLD level, and then the authoritative level. So the authoritative level is where the organization having hosts and IP assignments right are keeping. Because once you assign IP to a particular machine with the host name, the organization add that to the authoritative DNS server. Okay, and TLD and root, now you see probably that they are just for everyone to connect and so that they can redirect. If you're looking for example, nslab.ntu.edu.tw, which is the next server you go ask, right? And you might go to .tw or going to .edu TLD server. But going further down, so they would the TLD server will actually point you further down to the authoritative server of the entry you're looking for. And that exact detail I'm going to demonstrate in the next video. Exactly how you resolve from a host name to its IP address. There are actually 2 ways.
So far, we've learned that there's a hierarchy in the DNS servers. There's the top, second, and the third level. And we also know that there's a proxy server there, always working on behalf of the client, sending the DNS queries. So let's try to explain further from the local server here, how the query is forwarded, okay, and eventually receiving a reply. And let's do that through an example. Okay, there's going to be a host trying to reach Gaia.cs, but before messages can go out, CIS, poly here, needs to find the IP address of Gaia.cs over there. And we're going to illustrate this form of query forwarding. It's called the iterated querying. Right? So what the local DNS server does is to contact the server in the hierarchy. And the server will reply with something like this, name of the server to contact. Okay, someone who might know a little bit better, but I don't have it. So messages looks like this. Root server might say, hey, I don't know about Gaia.cs.umass.edu in particular, but you may ask, hey, the top level domain server for .edu. Okay, someone knows slightly better than I do. Okay? But I do know someone who knows better. Right? So that's the general idea. And so the process goes. Client here issuing query. Local DNS server now forwards the query first to the root. Root returns the IP address of the .edu TLD server. Therefore, the local DNS server could re-forward the query to .edu TLD DNS. DLD DNS does not know the IP just yet, but top-level domain DNS does know the IP address of the authoritative DNS server, so that will be sent back. And the local DNS server sends the query the third time, okay, to finally the authoritative DNS server. And finally, the IP address for Gaia.cs comes back to the local DNS server. Local DNS server forward that back to the requesting client and be happy about it. Recursive query is the second form of doing the query. So local DNS server here will forward only to the root, okay, and not contacting DLD, not contacting the authoritative DNS server. And it will be the root's job to find out what the mapping is. And root doesn't really know the mapping of Gaia.cs.umass.edu. So he forwards the query to TLD. TLD forwards to authoritative DNS server, and finally the IP address traverses back. And root DNS server here sends back to the local DNS server. Right. Can you see an issue with this? Yeah, so this way of querying puts burden on name servers that's high up in the hierarchy. There's going to be a lot of query comes to the root, and there's going to be a lot of queries coming from the root to the TLD, although the load on the authoritative DNS server remains the same. Right? So heavy load at the upper level of hierarchies, not good. Keep in mind, there are only some tens of root DNS servers, physical root DNS servers. If everyone is sending the queries always to the root, we could quickly bring down all these root DNS servers. And that's not really a viable solution. Therefore, recursive query is an option that we try to disable at the local DNS server.
All right, so it should be relatively clear to you now what the DNS is doing. Essentially, there are lots of these mappings. They need to keep the mappings. And these mappings are to allow all machines around the world, all services around the world to query. Okay. So there needs to be a server architecture there allowing reliable query, reliable response of these queries. Good, and that takes us to quiz 13. Okay, so quiz 13 here is a rather open quiz. Okay, consider this. Okay, some of you, I don't know about you, but some of you might be thinking it's time to get real. Okay, you decide that this is enough college education for you. All right. Have you thought about this before? You know what? I think Bill Gates, Mark Zuckerberg, okay, many of these guys, I think probably Steve Jobs as well, at some point during college think about this. And some of them decided that, hey, they are better off going somewhere and start something that they want to do. Okay, so hopefully that some of you feel the same. It's time to get real. And for those who don't have this idea, pretend that you do feel like what Bill Gates or Mark Zuckerberg were thinking. Hey, college education, is this really useful? Okay, you question that. So, hey, it's time to get real. Okay, and you think Petbook is totally better than Facebook. Okay, it's a social network service for pet animal lovers. Okay, instead of using your own face, okay, as the front photo, the profile photo, you use your pets, okay, your favorite animal's picture as the profile picture, okay. So Polly there is showing, a way of the look of such a pet book service, okay. Okay, so you know that it's very similar to Facebook. But you know what? When Mark Zuckerberg is building a Facebook service, he needs to think what you are asked to do. Being the CTO, in addition to the CEO, CFO, and being the COO, you need to try to architect your system. Okay? You need to try to structure the Petbook server network so that, hey, you got users. If one user is asking one pet page, okay, for example, pollys pet page. Pollys pet page is stored somewhere, right? Someone asking for pollys page will be querying that, okay? Much like DNS, name IP address mapping is stored somewhere, and someone out on the internet might be querying for that page, right? So DNS has a server network designed for this pet book. How are you going to build a distributed pet page database such that you allow anyone around the world to query a particular page? All right, so how would you structure the pet book server network and direct the pet page queries so the server load is balanced and the delay is low? All right. Now, hey, you have several reference designs already, right? So you heard about HTTP, how HTTP is structured as a system, allowing web page query, web page download. You heard about FTP, right? Allowing file query, file download. You heard about email, right? Yesterday, allowing forwarding email, isn't it? Okay, and response from saying email forward complete. So among all these and today DNS, right? DNS is probably the most complicated. Would you prefer modeling from each of these services, each of these protocols server network for pet page, or a combination of them? Okay. Now you see that this quiz is very open. You are asked this, being the CTO, okay, funding a pet book startup like this. How are you going to architect your server farm, server center, data center? And I here say server network. Okay. Allow Polly to elaborate a little bit more. Okay, you see here, this is again the quiz. Oopsie. This is HTTP, right? Structure very simple. There's no server network. There's just a server, HTTP server. So the network is the most simple one. Okay. So client send query to server. Server respond with the reply. This is what SMTP, the protocol supporting email. Okay. So there's a local mail server there. Okay, collecting emails from the local clients. Right? And the local server there will gather the email and then send the emails to a particular destination receiver mail server as a bunch. Okay. So you see that the structure is a little bit complicated. More complicated than the simplest one HTTP is using. Now today, you see this. Oh, again, we have a local DNS server, which is, again, to gather requests, queries from local clients. And then working on behalf of these clients, sending the real query to the servers where we store the real data entry. But in DNS, you see there are 3 levels of hierarchy: root, TLD, and then authoritative DNS server. Okay, so the server side is bigger than what we see in SMTP, HTTP. So you see here, from HTTP to email, we see the client side of the network gets expanded a little bit. Okay. From SMTP to DNS, we see definitely the server side, the data center side gets expanded. Now let's try to abstract, okay, what we see in these 3 different applications the network structures are. You see this, right? Client server, very straightforward. One client, one server, simple architecture. Second, having a local proxy here serving multiple local clients, okay? And the last one, you have also a hierarchy. You blow up the server end of the whole architecture, and so that you can scale up the service and make the service robust and potentially shorter delay, isn't it? Okay. And also potentially balance the load, right? You remember when we talk about DNS, just last video, there's this iterative query that we could lower the load of the root server. All right, so now with these additional information, okay, let's come back to quiz 13. How are you going to design the server network? Of course, you can also design the client side for the pepbook. Okay. Find your teammate. Okay. This is a long question, and I think we are in the break time now. So you do have plenty of time to discuss. And let's see. Oopsie. Come back here. Yeah. And let's see how you guys come up with an answer. So it's 11:14 now. Let's resume the lecture and come back to check at 11:24. Okay. Find your teammate. Discuss. All right. So definitely, if you wish to do it more DNS way, why? Okay. We do have criteria here. So that the server network can help direct the page queries so that the server load is balanced and the delay is low. So justify your choice such that the load will be balanced and the delay will be low. Good. So let me go to the Slack site and feel free to type up your solutions. And I'll probably need to go to the restroom, and I'll be back real quick, and we'll resume the lectures in 10 minutes. I see that you guys listened. Very good, guys. So we do have 1-2 minutes time. So Polly is very curious. What do you think is better? Trying to be yourself or trying to be perfect? Yeah, I know it's easier to be oneself. It's harder to be perfect. But if you think about it, it might not be better being perfect. And by the way, Polly's range of whether you do well or not is very wide. So it's okay to be yourself. Perfectly okay to be yourself. All right. Good. So let's check out what you guys have in mind here. You know what, Tim? You paid attention. So Tim followed DNS very well and knows that if he wants the pet page queries to go short delay, very balanced, then must use something like DNS, more extensive, right? Because when you have a hierarchy, then you can redirect the query so that the entries are stored, okay, here, there, everywhere. All right, and I think Jia Hong is saying something similar. Wait a minute. Okay. To have servers in different regions storing the pet pages. For example, one server in Taiwan is storing the pet pages from users in Taiwan. And then there's some top-level domain, pet page query server, right? Or root, pet page query server. So queries go to the root and see that, this is querying a Taiwan user. So, hey, you go query the top-level Taiwan server, Taiwan user server. And then finally, go to the real server storing all the mappings for Taiwan users. Very good. And Yun Tong here, Team 4, is saying more. Okay, so to view others' profile, I think her choice, or Team 3's choice, is similar to Tim and Jia Hong's. But Team 3 think a little bit further. Hey, in Facebook, right, we have also messengers. Okay, so there are other side services, okay, in addition to looking for people, looking for interesting pets. So yeah, for the part looking for interesting people to make friends with, or interesting people that you are already friends but you are not connected on pet page, right? So you might do messenger. Okay, for messengers, you could do SMTP using protocols like SMTP indeed. If one is only viewing your own post, it's just to download a post, HTTP. Yeah. So I think Team 3 is saying that when Petbook is gonna be extended broadly, much like Facebook, okay, with also direct messaging, then they would use a combination of these protocols, and different protocols will be used for different part of the services function. Okay, Wei An says, okay, messaging and DNS for the page queries, for the pet page queries. Team 4, SMTP, to send direct messages to each other, because this is a little bit similar to email, isn't it? HTTP, to get the posts down, but to find where the pages are, DNS. Using DNS to get the IP address of the server storing the web pages, and then HTTP to download the web pages. And if you are sending direct messages, SMTP. That's a sound story. Very good. Okay. So key point here is you want to provide an answer that has a sound story. Huaizhi here, DNS for the major framework. Well done. Well done. Okay. And Guanyu. People pages below. To use DNS. Yeah. Alright. So there is a higher level like root petbook server, okay, or top level domain or top level petbook server, and then you have the real server storing the content. Good. So, Guanyu, as you type all these up, then I know that you follow DNS lectures perfectly well. Very good. And you get you see the structural differences also between the different protocols design. And they differ because of the nature, isn't it, of the content they are serving. Very good. So I think now you guys know exactly why there's application layer chapter and why we talk about multiple applications and their protocol designs. Because from contrasting the design differences, okay, by knowing the nature of the services, you also know better, right? In case you need to design something that needs to contain a service that's a little bit similar to web page download, that is a little bit similar to email transfer, that is a little similar to DNS, a name IP address mapping, then you know, right? Reference architectures you could use. Very good. That's the point of the quiz and the point of the lectures. Well done. And very good. I'll come back to grade the rest of the quizzes later, and let's move on to the second part of DNS. We're not yet done. Okay, it's an actual protocol storing actual mapping entries. Now let's take a look at exactly how these mapping entries look like. Okay, the data records.
DNS servers also cache data. And this is not the first time we hear this term caching. The first time is when we were talking about web caches, isn't it? So web cache there stores web objects so we could reduce delay. We could save some network bandwidth. You see here, DNS, for the same purpose, also caches IP, name, mappings. Okay? The goal is also to reduce delay to save network bandwidth. So you see, caching is actually a very general technique for data transferring services to try to avoid repeated download. Let's go on to DNS caching. So each of these mapping will be stored at the name servers once they acquire them the first time. So these entries will be there on the server's disk for some time. So the interval is called the TTL. What it stands is time to live. So during this time, the entries stay. Once the time expires, the entry is timed out, removed, okay, from the entire disk. So an example, a local name server might store the mapping for a top-level domain server so that the local name server doesn't need to go to the root name servers a lot. Okay? Again, trying to conserve the root server's capacity. Right? And the cache entries may go outdated. This is happening when the entry is not yet timed out, but the host there is already changing the IP host mapping at the authoritative DNS server. In that case, the clients worldwide will continue to get the old mapping, the out-of-date mapping, until 2 days later. This is usually the TTL of DNS mappings are set to by default. So 2 days later, the clients get the new mapping. So that's why we don't change the hostname IP mappings all that often, because during these 2 days, your customers will have trouble reaching you. So Dns caching, this is another protocol. It's defined in this RFC 2136. And by the way, the body, the community defined all these internet protocols. Okay, writing all these RFCs is called the IETF, the Internet Engineer Task Force. Let's take a closer look at the entries that DNS servers are storing there. They're called the records. Okay, well, to be more precise, the resource records. Okay, and each look like this: a tuple of 4 elements. This is usually the host name, and this is the IP address, and this is TTL, the time these entries should stay on the server. What we haven't talked about is this type. There are actually 4 of them, not many. Let's look at them each a little bit closer. So first is type A. It's the most classical one, which says hostname and the name, and IP address and the value. Essentially, this is the query, and this is the answer. Querying for this host, answer is this IP address. Second type, let's go here, the C name type. What C stands for is the canonical name. So what this does is corresponding to the second service we mentioned way earlier when we started talking about DNS. So it's doing what? Alias, the name alias service. So what it does is here, the entry there, name is the alias, the Q short one, and the value is the actual name, the canonical name, the real name. So here we have .ibm.com, cute and short, easy to memorize, but the actual name for that machine should be this, server is backup to .ibm.com. Right? So value is the canonical name. Third, let's look at this type, the MX type. So this is mail service type, and this corresponds to the third service that DNS provides. Name is a domain. Value is the mail server for that domain. So name here could be gmail.com, and the value will be what? smtp.gmail.com. Straightforward. Last type we have not yet talked about. It's actually not quite the fourth service that we mentioned about DNS providing. It's actually called the authoritative name service entry. Right? So the name there is a domain. Okay? But it's not the top level domain. It's usually the second level domain. The value is the host name of the authoritative name server for that second level domain. So this is for the TLD servers to store all the authoritative name servers for all these subdomains. Right? So NS type entries are mostly in the TLD servers. Next, the Dns Protocols Messages. So the servers exchange just the query and the reply messages to each other. They are in the same format, which is exactly what I'm showing here. There are 2 parts though. From here and up, this is the message header. From here and down, the data part, where the actual mapping, actual entries are being carried. Now let's focus on the header a bit more. The first field is called the ID. It's 16 bits long. It is used to identify a pair of query and reply. Right? Next in the flags, then you identify whether this is a query or this is a reply. So this is how server know that, okay, this reply is for a query that carries the same ID. In the flags, you might also see a certain client is saying that, can I do recursive query? In the flags, you might also see certain DNS server saying, no, let's disable a recursive query. And coming from the authoritative DNS server, you might see this flag being turned on. The reply is authoritative. There are 4 other fields in the header, these. So these are specifying the number of questions, number of answers, number of authoritative replies, number of additional informations. Now these are to serve the purpose down here in the data part, because the number of questions a DNS message can carry is variable. Now in order for the receiver to know how many lines, how many records it reads, it looks up here to find out, and reads up to this point, and then to the next part. So that you will not be confusing a regular reply with an authoritative reply. And next, let's focus a little bit more in the data part. Okay, so in the question fields, you will only see this, the name and type in a query. That's all. There's no value, there's no TTL. In the answer entries, however, then you see the full RR, full resource records. Authority here carries records for the authoritative DNS servers. If you have also the full RRs, it's just that those RRs are the authoritative server RRs. Last is just additional information. I see rarely this part of the data being used.
All right, so these are the things you want to know in case you want to implement your own local DNS server, for example. You need to know the messages format in order to be able to communicate with the other servers in the hierarchy. And last video about DNS is this. Before we play the last video, there's a very interesting question. Okay, this is from Xue Han. So the question was this: hey, even in iterated query, the low is balanced, but delay is pretty long, right? It's not exactly sure because the local DNS server asks the root server asks you to talk to the TLD server then finally tell you to go to the authoritative DNS server. That's what, 1 round trip, 2 round trip, 3 round trip before you get the result. Yeah, that delay is long. But you know what? In the video we just finished hearing, DNS cache also these mappings. So in the local cache here, after you ask, for example, www.google.com, and you have already find the IP address of www.google.com, that mapping is going to be cached locally in the local cache. So if there's another guy nearby, another local client is looking for the IP address of www.google.com, real quick, from the cache, there's a match. All right, so that's why also DNS query gets also shorter. Now, for pepbook, how do you ensure that delay is shorter? Do you cache the pepbook pages? Of course, you can try to do that. But you see that it's a little bit tricky, right? Implementing a local cache for pepbook. All right, so that was the question, and now we can play the last video. Last video is to talk about more that if you are creating your own company, okay, and you are starting a mail server, a web server, so that your customers can write you email. Potential prospective customers can check out your company's website. You need to also set up an authoritative DNS server for your own organization. So exact steps that you need to follow. And also DNS is under attack a lot because you see that it's a very important service. If a company's authoritative DNS server is under attack, well, people will have trouble coming to your company's website or writing you emails. So that is what this video is about.
Now let's try to put our knowledge into use. So here the scenario is you need to set up your network for a startup. Network utopia. All right, so 2 things you need to do. First, register your domain name with the DNS registrar. Now, being a .com, you talk to this company, Network Solution, who maintains the .com TLD server. Right? Second, you provide also the name and IP address mapping of the authoritative DNS server you'll be setting up. Okay, so there could be a couple of them just in case the first one failed. There's a backup. At this point, the registrar there, the network solution there, will try to insert 2 records. One is, of course, the name and IP address mapping. Second is the domain name and the host name of the authoritative server. So you see here, name to IP address is the type A, the classical one. This one here is the NS type, the authoritative type, where the TLD stores domain name and the authoritative DNS server. Now, back home, you need to set up a couple of these authoritative servers for sure. But inside these authoritative servers, what do you store? Well, if you want a web service, you need type A entry that keeps the name of the web server and the IP address of the web server. If you wish to have email service, then you need to set up an NX entry maintaining the mapping from the mail domain to the mail server's host name. And maybe the IP address of the mail server entry, that's another A record in the authoritative server. All right, so that's how you get your customer to see the IP address and therefore being able to visit your website. Attacking DNS, this is the last bit of DNS. So we're going to talk about attacks in 3 parts. First is attacks targeting the hierarchy of the DNS. Second is to target more the client who need DNS service. Third, then is to exploit the DNS service to try to pull off attack for some other targets. So let's go back to attacking the hierarchy. So a hacker could actually hack down a number of machines around the internet and have these machines bombard the root servers with lots of DNS queries. Okay, so having very few root servers around, this can potentially be dangerous and bring down the DNS service entirely. But nowadays, now it's hard to pull off, mostly because the local DNS servers will cache the TLD servers. This allows all the local servers to bypass the root server entirely. Right, so there's not much traffic going to the root. If the zombie machine sends a lot of queries, chances high that they only go to TLD instead of the root. Not to mention that one could set up firewalls nearby the root servers. So those very few root servers are well protected in a way. Now, attacking the TLD servers then is more feasible, all right? Because queries then all go to TLD these days. Good, so it's more dangerous. But the thing with the TLD server is that the number of these is way higher than the number of root servers. So the hierarchy there is pretty robust, to be frank. The second type is the redirect attacks, but I would rather call that this is attacking the user of the DNS service. First is the man-in-the-middle attack. What the hacker does here is just to intercept the queries. Therefore, it's not going to reach anyone in the hierarchy, and therefore no answers back to the users. Second one, on the other hand, I think is meaner, DNS poisoning. So the hacker there is actually sending false replies. So when local DNS server caches these replies, the users will be thinking, "Ooh, I thought I'm going to the google.com, but it's actually going to a hacker's website." Not very good. So nowadays, network admin for the local DNS servers needs to be careful and check the sources of these replies. Last one, exploiting DNS for DDoS. We actually hear about this already. So this is in chapter 1, I believe. Okay. So people are sending queries. Hackers can spoof these queries and replace the source address, with the IP address of the attack target. As a result, the servers in the hierarchy will be all sending replies to this guy here, and therefore denying this machine here to go out and reach the rest of the internet. But this is also a bit hard to do because you have to hijack enough of these queries. You need to spoof enough of these queries. Right? So you need amplification in order to make sure that the service is really denied at the target IP. And that's all for DNS.
All right, so I have to apologize for chapter 1. We don't have that much time to talk about the attacks on the internet, but there is a video on the channel that you can find. I think it's at the end of chapter 1, I think 1.7 or 1.6. There's a video talking about general internet attacks. So that attack DDoS of DNS server or exploiting DNS server was actually also mentioned in that video. Good, so DNS, what do you think? Very interesting, isn't it? Yeah, it's less known. You are using it, but you are less aware of it. But the structure of supporting this name IP address mapping is quite elaborated. Now we go to P2P.
To be honest, this is one of my favorite sections in chapter 2. All right, so P2P architecture. As opposed to the very simplistic client-server architecture where we have always-on servers, in P2P, there's no more always-on servers. Instead, we just have these arbitrary peers directly connecting to each other, communicating to each other. As you see, these peers are very likely mobile end systems. So the connectivity there is intermittent, meaning loosely connected, on and off, on and off. And the IP addresses to establish physical connectivity can also change over time. So it's actually hard to maintain a fully connected session as a user moving around, for example, on NTU campus. So we'll talk about two applications. One is for file distribution. The other is for voice service, voice over internet service. So the application for file distribution is Bittorrent, and the other one is called the Skype, an internet telephone service. We're not going to talk about applications in video streaming, but there are actually quite a number of these video streaming systems in the early years that works in this peer-to-peer way. So for example, this one, Kankan from China, that's Mandarin Chinese, meaning take a look. It was a very well-established service. Okay, before we talk about all these P2P application examples, let's talk a little bit more about the benefit of shifting from the client-server paradigm to the P2P paradigm. And there must be a reason why people choosing to do P2P instead of client-server. And we're going to use an example, very simple, to transmit or to distribute a file from one server to n users. Each of these users will be limited in terms of the uplink as well as downlink capacity. So look over here. This is peer I. Okay, so its uplink capacity is called UI, and downlink capacity DI. Okay, so the same fashion you see therefore for user 1, uplink bandwidth being U1, downlink bandwidth being D1, and same for user 2 and user N. The server is over here. The uplink capacity is US. Well, therefore, the downlink capacity is DS, although that we're probably not needing it in the calculation. Right. So file, one big file, size being big F. So this is the setting. Now let's calculate the time it takes to distribute the file to all end users. First, assuming client-server model, meaning server here we need to upload a copy and distribute it to each of the clients. If the uplink capacity is US, therefore the time to send one copy will be F over US, and to send n copies altogether, NF over US. And this is the term that we have here, because the overall file distribution time will be limited by the uplink capacity and the minimum client capacity. So this is the case where the server is the bottleneck, and this is the case where a client with the minimum downlink bandwidth is the bottleneck. Now, the client carrying the minimum download rate, let's assume the value is dmin. Therefore, the download time is F over dmin. The smaller the dmin is, the longer the download time is. And therefore, you see, again, in case the server is the bottleneck, the overall distribution time will be bounded by this guy. If the client is the bottleneck, the overall distribution time will be bounded by the F over d. Now, that's considered an n that's increasing over time. Right? Talk about the scalability of the system. The file distribution time, how does it scale with n increasing? Well, this term suggests the overall distribution time will increase linearly in n, while the minimum bandwidth for downlink might not change all that much. So, potentially the overall delay, if we change n, is growing like this. Now, the same, calculating the time for file distribution, but this time in the P2P model. Meaning, hey, this is one of the peers, and each one of these users is also one of the peers. So they could be downloading a copy from the server, but they could also be uploading a copy for another peer. Now, the server transmission time, this part now, the optimum is just to send one copy uplink. So F over US. Client there, in case it's the bottleneck, it's going to be bounded by F over dmin, which we explained. And clients overall as aggregated system, must download NF bits, and the maximum upload rate is the sum of all the uplinks for all the users plus the uplink capacity of the server. Right? So in a way, the file distribution time here for a P2P system, it's bounded by either bottleneck at the server, bottleneck at the client, or bottleneck as the system as the whole. If we want to download NF bits over this much bandwidth entirely, right? So we have the server being the bottleneck case, one of the clients being the bottleneck case, and the system overall being the bottleneck case. So NF bits that needs to be passed out, over the entire capacity, entire uplink capacity of the system. So the distribution time bounded by one of these two terms. All right, now consider again, if n is increasing over time, right? The scalability of the P2P modeled file distribution system. Which of the term you think is going to grow with the n? Yep, this one over here. Right? It also grows linearly with the n. But if you look closer, when the number of users also increase, this term also increases. Yeah. So does this. And each peer brings service capacity. If you recall, this is also what was talked about called the self-scalability, a nice property of P2P architecture. Okay? As a peer join, right, the peer demands service, but the peer also contributes its own uplink capacity, okay, to help others to download. Okay, so this grows linearly with n, but this also increases, but not quite sure if it's growing linearly. But overall, it's going to be better than what? The linear growth. So the growth is probably more like this. Let me use a very simple scenario to contrast quantitatively the differences between client-server mode and P2P mode in terms of the distribution time. Right? So the scenario goes as this. The client's upload rate is small u. And if we want to upload the file over this client link, f over u. And let's say that that's 1 hour. And the server uplink rate is 10u, 10 times higher than the client's uplink rate. And let's assume the downlink capacity of all the clients are just so large, much higher than the server uplink rate. Right? So bottleneck is actually here, the user uplink. Now, think. Let's assume that there are 10 users. Okay? In client-server mode, what is the distribution time? So let's see. 10 users, 10 copy of the file, and the uplink capacity of the server is 10u. Therefore, what? F over u. And this is 1 hour. So in this case, yeah, the distribution time is 1 hour. Clear? Now, in P2P mode, let's see. We have what? 10 files, 10 copies of the files that needs to be downloaded overall. Right? And what is the total uplink capacity of the system? So user has 10u. Each client has what? 1u. So 10 of them, also 10u. Altogether, 20u. And how much is this? Half of f over u. And this is what? Half an hour. And is that right? It is right? In P2P's case, 10 users, only half an hour. Okay? So you see, the growing trend, linear in client-server mode, but sub-linear in P2P mode. And this illustrates this characteristic of P2P system very well, self-scalability. Right? And this is the big advantage of running an internet service in the P2P architecture over the client-server architecture.
All right, so that's the main difference between P2P and the traditional client-server model. In P2P, you can exploit all peers' resources. Okay? Not just the uplink bandwidth that we keep talking about in the video. You can also exploit other peers' hard disk space. Okay. All right, so that was P2P and talking about the performance of using a P2P architecture can potentially be better than the client-server architecture. Now, during the video playing, there was a question about HTTP. And this is related to DNS. Okay, so it's from Guan Yu. So he was asking, so you guys probably started reviewing chapter 1 and chapter 2 for the exam. So in HTTP message, right, there's a field called host, right, and then you give it the host name, give it a host name there. So does the host name there need to work with the DNS server? So for example, if you give you need to give a legal host name so that you can find an IP address for that host. Okay, that's a very good question. You see, DNS is actually triggered before, in parallel of generating that message. In fact, okay, So when you click on a link, DNS query is already fired. Okay, and that DNS query, inside of it, the host name is indicated by the link's URL, the host name part of the URL. And so once you hit that, your browser would actually ask the DNS, local DNS server to query for the IP address of that server, of that web server. And what you're seeing there in HTTP message is actually a field. And all these things, although they are header of a message, these are still in the data you send out to the server. That is, you already know the IP address of the server. You are generating a message you send to that server. So whatever that's after the host field doesn't need to be a real host name, if you think about it, unless the server or the machine receiving this HTTP message is using that host name for some further purpose. And that machine will later on query the IP address of this machine. Otherwise, it's actually okay to give a random host name there. Okay, the server side there does not need this in order to send a response back, because you have already established a TCP connection before you can send the message, and the reply knows already where to send stuff back. TCP connection is already established. Okay, so it's a little bit weird, but that host is there so that the server can know a little bit more about what's going on. And as to what value you fill in for the host field, for a regular browser, there's a certain way that everybody agree doing. But if you are writing your own browser, you don't necessarily need to follow the agreement, the implicit agreement. So according to HTTP protocol, there's no strict regulation what you put there. So the server oftentimes won't take this too seriously. Okay. I hope that addressed the question. And next, there are two videos, but both of these videos are about Bittorrent, the most used P2P application until Bitcoin, I guess. So let's check out how Bittorrent works.
First example is Bittorrent. The way the file is distributed in Bittorrent is, instead of sending one big file at a time, it's divided into smaller chunks, 256 kilobytes per chunk. And the peers in a torrent actually sends and receives these file chunks. So here's to illustrate the P2P network. Okay? And each of these is a peer. Okay? And the group of peers form a torrent. Okay? And they exchange chunks of a file. So BitTorrent. Now, there's one more entity. It's called the tracker. So this machine here is actually to bootstrap the process of having a new user joining or a new peer joining the torrent. So when Alice arrives, for example, what the system does is to first contact the tracker, and then tracker in return, giving Alice a list of the peers. And this is the initial set of peers that Alice will connect to. Now once Alice is connected to the torrent, then Alice can try to explore other peers and then establish connections to these other peers. So tracker here is to bootstrap the initial joining process. Furthermore, about the operation of BitTorrent. A peer joining the torrent, yeah, you've heard it earlier, right? Contacting the tracker to get the initial set of peers. And those peers that are connected to Alice will be Alice's neighbor. And Alice at the beginning has no chunks, but over time, Alice will accumulate these chunks and eventually growing into a complete file. Now, the general operation is this. Each peer will be downloading the chunks while they are also uploading the chunks to other peers. And the peer and peers exchanging chunks, the pair could change from time to time. So they may change the peers with whom they exchange chunks. And the peers might just go away and come back in the middle of the exchange. That could be a bit disturbing. There's a special term for it called a churn. Hopefully there's less amount of these churns, but sometimes it's not really controllable. And in the end, once the peer has the entire file, for a selfish peer, he or she might just leave the P2P network entirely. For those who are more considerate, they might remain on the torrent. The part that Polly finds the most interesting about BitTorrent is this. the strategy to request chunks, and the strategy to send chunks. Let's talk more about the requesting strategy first. The setting is this: given a file that many of the peers are looking for, so they're downloading chunks for the file. At any given point in time, because they're doing the downloading independently and they might be connecting to different neighbors, they might not know each other, so at any given point in time, different peers might hold a different subset of the chunks belonging to the file. Right? And the way it progresses is each peer then will periodically query the neighboring peers. So asking neighbor 1, neighbor 2, and neighbor 3 for the set of chunks neighbor 1 has for that file, neighbor 2 has for the file, and the set of chunks neighbor 3 has for the file. Okay? So it's kind of an inventory check. Now once the peer receives all these inventory check reports, the peer begins to count which chunk is the rarest in the P2P network. And the peer begins to download from the rarest that he does not quite yet download yet. So that is the requesting strategy. Now if you think a little bit more about it, why rarest first? If I tell you, look back at the previous slide, the issues we might run into are these, right? A peer might come and go. Right? So as they move from one subnet to another subnet, it might get disconnected, the IP addresses might get changed. If it's in the middle of the download, those chunks will disappear from the P2P network. Also, right, when some peer finish downloading all the chunks to a file, and if the peer is selfish, they might just leave the network entirely. So in a P2P network, real users will all have this anxiety of not being able to find a specific chunk for a file. And that is also when Bittorrent downloading can go really, really low. It's not because there's not enough capacity, but it's more. Certain chunks are no longer there on the network. Okay, so it's actually quite important this rarest strategy is implemented on a P2P network like this. And another aspect that's interesting is the sending strategy. And I love the name, tit for tat. It sounded kind of fun. Right? The way it works is also very simple. Alice here as an example here, she will send chunks to others that are sending back to her at the highest rates. Okay? So, hey, if you're generous to me, then I will be generous to you. Okay? Eye for eye, tit for tat. But this simple strategy might create this problem. Other peers are not sending at the highest rate. Will be choked then. These guys might not get a chance of downloading certain chunks from Alice at all. Right? This is actually not quite that good. So Alice will reevaluate the top 4 every 10 seconds. So those peers who discover that they're choked, they're not downloading any chunks, they might decide to contribute more uplink capacity. Therefore, as a result, they might get some chunks from Alice back in the next round, the next 10 seconds. Okay, so this is the general strategy. Okay, share your uplink bandwidth, then I share mine. But this might not be a good thing either, because some of these peers might be very non-resourceful, meaning they have very, very low uplink capacity. As a result, they might always come up short here in the competition for the highest rate neighbors. So every 30 seconds, Alice will be very generous, okay? And not look at the sending rate coming from the neighbors, but just randomly pick one of them and start sending chunks to them. So optimistically unchoke, okay, a particular peer. Now the newly chosen peer will join the top 4 and receive chunks from Alice. Right? But this is done at the lower frequency, only every 30 seconds. Right? So mostly favoring those who are contributing more bandwidth for uplink purpose, but every now and then, not bias on the uplink capacity of the peers and openly share. Okay? Interesting, isn't it? And let me animate tit for tat here. So Alice here optimistically unchokes Bob. So Bob could be a newcomer into the network. Okay, Alice might randomly discover, okay, there's this guy Bob there. Alice begins to send chunks to Bob. And Bob there says, wow, thank you for all the bandwidth, all the chunks. Okay. And begin to send, also at a high rate, back to Alice. So mutual appreciation at the end. But Alice needs to be optimistic at the beginning, right? Trying to have faith, trust that whoever receiving the data would appreciate the effort. So higher upload rate finds better trading partners, okay? And so you get files faster this way.
Right. So that should take us to quiz 14. But you know what? We don't have time for really quiz 14. So quiz 14 here will be a quiz that for week 6 for next week. So I will update the assignments due this Saturday and saying that the quizzes due is excuse me, are only quiz 12 and 13. And for the remaining time, please come try out your camera. And those who have questions that you want to ask, feel free. Type them up on Slack or type them up on chat. Sorry that Polly drank and then I choke. I'm choking a little bit. Okay. So now that's skip quiz 14. In fact, next week when we start lecture, we'll start from quiz 14. Quiz 14 is already on the Slack quiz 14 channel. Now, if you want to work on it already, feel free. Feel free. All right. So remaining time is, yeah, that's test drive your camera. All right. Okay, nice start, SSJ. All right, that seems to be working. Good. Yeah, so maybe I should stop the stream, so that you are not broadcasted to the rest of the world. So 1 second, guys. Okay, Liang Xin and everyone. Let me stop the stream now. Otherwise, you guys will all be recorded. Okay, stopping the stream. And once I stop the stream, please come try out your camera.